Okay, let's move to this clampers operation. Clampers. So last time we discussed about the charging and discharging effect of the capacitors. So if we graphically illustrate it, it's something like that. So this is the charging and this is the discharging. So this is the voltage across the capacitor. So this is the voltage across the capacitor and it's charged up to kind of a V naught value. Once you apply a voltage across the capacitor, so this capacitor charge up to V naught. So V naught is the maximum voltage that that applied across the capacitor terminals. So V naught is the maximum voltage applied across the capacitor of the terminals of the capacitor. So so then we found that once you apply this external voltage, this capacitor gets charged up to V naught, and it will take a certain amount of time to charge it to maximum. So similarly, once you charge the capacitor, and if you connect it to a kind of a resistive load, whatever the stored energy is simply released or discharged through the resistive load. So then this would be the discharging process of the capacitor. So this is actually the discharging process, and this is actually the charging process. So and so for these two cases, so we will discuss these concepts deeply in circuit analysis. So we define a parameter called tau, which is actually known as the time constant of the circuit. Time constant of the circuit. So so if we mathematically define it, so the time actually required this capacitor to drop this initial voltage by E. So E naught by E. So this is the time for the capacitor to discharge. So for example, this capacitor is initially at the voltage of V naught, and if it is referring the discharging process, so then whatever the voltage is simply decreasing and converges to zero. So there's a point where that initial voltage drop down by E factor. So this is the point where this initial voltage simply drops by E naught, E. So this particular time is called as the time constant. So this is time constant. So similarly, you can have kind of like so this is similarly you can have a kind of a value here at T naught. So this is actually this capacitor is charged up to a value where this the V naught over E. So this is the time constant. So this time constant, for example, if this time constant is greater than 0, which means like it takes longer time to charge or discharge. So for example, if this tau is large, so it's something like that. So this is your initial voltage. So This is now tau V naught by E. So if you increase this, if this tau is reasonably high, it means like it takes quite long time to discharge. It takes time. So ideally, if this tau goes to infinity, what happens? So then if tau goes to infinity, what happens? So so we can claim that if tau goes to infinity, so this whatever the stored voltage remains as it is, and this capacitor never discharge. So when tau goes to infinity, so this time is simply moves to the infinity. So then this discharging process takes infinite time to converge to zero. So then we can argue that for the scenarios where time tau or the time constant is infinite, so you don't see any discharging process. So from that, so we can argue that if tau is pretty much high, no discharging happens. No discharging happens. Similarly, so we can argue for the charging as well. So if your charging process takes too much of time, so it means like initially it's something like that. So this is your tau. I think this is your tau. Now let's think about the scenario where tau goes to infinity. So in the second case, now it's something like that. So then tau getting increased. So we'll take another scenario. So then tau moves to this. So if we take another scenario, so then tau moves to this. So likewise, if your tau tends to infinity, so then we can argue that for this particular scenario, this capacitor needs infinite time to boost its voltage to V0. So if this is V0, so it takes infinite times to boost its voltage across the capacitor to V0. So then ideally speaking, you can see a kind of a charging process, never charge. So from these two concepts, we can basically build an argument if ideally if t goes to infinity, so time constant, this is a time constant, goes to infinity, you can see charging or discharging of the capacitor, never charge or discharge the capacitor. So this for the circuit contains resistors and capacitors. So we call it as RC circuits. So the time constant tau would be equals to the product of R and C. So if you have multiple capacitors and multiple resistors, we know that. So you can simply simplify the circuit to a circuit where you have a single equivalent capacitance and a single equivalent resistance. So then the time constant of the capacitive RC circuit would be ideally the product of R equivalent and C equivalent. So if you have multiple capacitors and multiple resistors, you can simplify the circuit where you have a single equivalent capacitor and a single equivalent resistor. So in that scenario, your tau time constant would be R equivalent into C equivalent. So this is your time constant. If you have RC circuit where you have resistors and capacitors in the circuit, So you can simply claim that the time constant would be the product of this effective R and effective C capacitance. So let's have like so we have RC circuits for this particular scenario. So if you have RC circuit, we know that the time constant would be the product of R and C, and if this time constant or the product of R and C goes to infinity, you can't see any charging or discharging process happen inside the circuit. So this is the ideal situation. So we can practically say that if this tau is pretty much large, so you can see that say that this you can see like you can claim that never charge or discharge. Okay, if tau is pretty much high, so the charging discharging cannot be observed. On the other hand, so most of the studies found that so this RC circuit or the capacitor needs 5 times tau time to converge. So what I mean by this, like, so we know that if it is a charging process, so initially the voltage across the capacitor is 0 and then gradually increase the voltage across the capacitor to its maximum. In this case, it's V naught. To converge into this V naught, it takes 5 times the time constant. So it takes 5 times the time constant time. So similarly, if this capacitor is already charged to V naught, it takes 5 tau time or 5 tau seconds to converge or discharge completely to 0. So it means like if you mark it like, so this may be the 5 times tau. So it converges to its maximum. Similarly, this may be the 5 tau. So this is a kind of facts found in practical circuit. So if the time constant or the product of RC is pretty much high, so we can argue that there won't be any charging or discharging happening in the circuit. At the same time, so we found that to converge the voltage to a certain value, so this capacitor needs 5 times the time constant to actually converge to its maximum or minimum. It takes 5 times tau seconds. Okay, so this is the basics we need to apply for this clamper. So we'll now consider a very simple circuit. So let's consider this circuit. So you have a capacitor here. So you have a capacitor here, and you have a load resistor and a diode. And let's assume like, so we are applying a kind of alternative DC source like this. So the peak values are V naught. So it's like that. So this is V naught and this is minus V naught. So this is your capacitor and this is your diode, this is your resistor. Okay. So let's consider this very simple circuit and see what happens to this capacitor. Okay, so I'll do a small change to this input. So later on you can realize what actually happens. For the time being, so this is your input voltage. Okay, so now this is the applied voltage to the circuit. And you have a capacitor which is actually at 0 volt because there won't be any charge across the capacitor. So the voltage across the capacitor is initially at 0. So we have a diode oriented like this, and we have a load resistor. So see what happens to the circuit during this negative and positive cycles. So let's think about the negative cycle first. So we have negative cycle first. This is negative, this is minus V. So then we have capacitor here, we have a resistor, we have diode, and a voltage like this. So this is your input voltage. So this is your input voltage. Okay, so this is the polarities of the diode. Okay, now we have a capacitor and a diode and as well as the resistor. Okay. Let's assume for the time being, so we have this capacitor and a resistor. So there's a circuit like for example, if you just think a situation where you don't have a diode, so then you have a capacitor and a resistor there in the circuit. So then we can say that there's a kind of RC circuit appear here. So for the time being, we'll assume that so the product of R and C into RL is pretty much high, very high. Okay, so the product of RL and C. So this is actually, so this is the time constant for this circuit. So if we simply neglect this diode, so you have a source here, so you have RL, so you have a C. So this is a kind of a RC circuit. So this is a kind of RC circuit. So for RC circuit, you can simply claim that there's a kind of a value called time constant, which basically gives a kind of insight about the charging and discharging rates. So it is actually the product of RL and C. So this is the time constant. Okay. So if we see for time we will just omit the diode, so then we can have a kind of a RC circuit. So this entire circuit is simplifies to a RC circuit where you don't have this diode at the. So then for this particular RC circuit, we can define a time constant. So the time constant actually gives a kind of indication about the how fast this charging and discharging happen. If this this time constant is very small, it means like it's immediately charged and immediately discharged. So for example, if this time constant is very high, very low, so this is this charging and this is the discharging. So it means like if this tau goes to 0, so you can it's immediately charged and immediately discharged. So if this t goes to infinity, so we know that it never charged and it never discharged. It never charged and it never discharged. So whatever the value stored in the capacitor remains as it is. If it is zeros, it keeps 0 voltage across the capacitor during that particular time. If it is like V0, it keeps V0 as it is. If the time constant is very small, so it immediately charges to its maximum and or else it immediately discharges to 0 within a negligible time. So this is the relation between tau and the charging and discharging rates or the time. So we can simplify a circuit where you have R and C in the circuit. So for this RC circuit, we can define a time constant. So the time constant would be the product of RL and C. So for the time being, we'll assume that this product or the time constant is very, very high. So now see, for this during this negative cycle, so this during this negative cycle, so we have applied voltage like this, the polarities are like this, so a minus cos, and so this is the diode orientation. So now with this diode arrangement, so you have voltage applied across this input terminal. So by looking at this one, so you can find two paths. So one is like you can induce a current flow through the diode. Okay, so we'll first find this. So what's the actual voltage appear across the diode? So from minus to plus. So like in the previous, we can simply remove the diode for the time being, and we'll evaluate the open circuit voltage across the diode. Initially, this capacitor is at 0 voltage because we didn't apply any voltage across the capacitor. So it has a 0 energy or 0 voltage. So then from this one, so once you apply Kirchhoff voltage law for this two, so we can simply say that the open circuit voltage, if you apply Kirchhoff voltage law, so we can simply say that, so initially the open circuit voltage equals V in, which is equals to V out for this case. Because VCT is actually 0 for this case. So then the entire input voltages appear across the diode. So like we know that there is a positive voltage drop appear across the diode. So hence D gets forward bias. Okay, D gets forward bias. At the same time, see like there's another RC circuit here. So there may be, so we apply this negative voltage. Once you apply this negative voltage, diode get forward bias. So this diode get forward bias. Again, we have a RLC circuit. So there's a RC circuit. So then, so we have a kind of a issue. So what would be the significantly impact to the capacitor? So there's a circuit or there's a path through a diode as well as there's a path through the resistor. So we have two paths. So we have this path and we have this path as well. So if we select the path through the load resistor, so we will get a kind of a circuit having this. So we will end up with a RC circuit where this time constant is pretty much high. So then from the initial assumption, we can simply say that this time constant is pretty much high means, so if we consider a circuit through this load resistor, so then this capacitor never charged because this time constant is pretty much high. Or else we can argue that time constant is high means that the load resistance would be comparably high. So then the other path is through the diode. So we know that if it is a kind of ideal diode, once we make this diode forward bias, it simply acts as a short circuit element. Short circuit element means zero resistive path. So then during this negative cycle, so this RC circuit RLC circuit is not come into the picture because RC product is very high. So then no current flow through RC circuit due to this high time constant. So this capacitor never charged through this RC circuit, and it basically charged through the that set. So then the current is actually flows through the diode capacitor circuit. So then this is not possible because this RC constant is high. So RC is pretty much high. So the only path possible is through the diode. So then we have a circuit like this. So we have capacitor here. So we have a short forward bias diode. So then if we assume that ideal diode, so it's something like that. So then here we can claim that, so this tau for this particular case is almost zero because we have a zero resistive part and we have a certain amount of capacitor. So the time constant would be pretty much low compared to the product between RL and C. So this is very small. So this is very small, and once you apply external voltage across the capacitor, it immediately charges to maximum. Okay, so now we apply V naught here. So it means, so you can see a kind of a current flow through this way, and this capacitor gets charged like this up to V naught. Okay, so then what happens? Actually, capacitor is immediately charged up to V naught during this cycle. So if you draw it, so this is actually immediately charged to V naught. So this is the voltage across the capacitor. Initially it's zero. Once you apply this negative voltage, diode gets forward bias, and it creates a very small time constant circuit, the product of C and the conductance or the resistance of the forward bias diode, which is almost zero. So then you have a kind of a circuit where we have very small time constant and it immediately charges to V naught. V naught is the voltage applied across the capacitor now. So this RL and C, so this RC circuit is not coming to the picture because the time constant is pretty much high. So you can't see any current flow through the RLC circuit, and the entire current flow through is through the diode. So then during this negative cycle, what happens is capacitor gets charged up to V naught in the polarity of this manner. So now we'll see what happens during the positive cycle. So let's think about the positive cycle. So then we apply this kind of a signal. Now the circuit is something like that. So we have a capacitor, we have a resistor, diode, and we'll apply this kind of voltage. So this is V in, which is equals to V0. And this is diode. So now, so once we change it to the positive polarity, this capacitor is already charged up to V naught. Okay. Now, so we'll see what happens to the circuit. What happens to the diode first. So similarly, we can claim that Here it's negative, this is positive. So this is the open circuit was. So if you apply Kirchhoff voltage law for this diode capacitor circuit, so we can simply say that we have V naught initially applied through the input terminal, and this capacitor is already charged up to V naught. So we have 2 V naught plus the open circuit voltage equals to 0. V naught plus V naught plus VOC equals to 0. So then the open circuit voltage is minus 2 times V naught. So this is the actual voltage across the diode, which is equals to 2 V naught, which is actually less than 0, kind of a negative value. So if we apply a negative voltage across the diode, we know that definitely diode get reverse bias. So now diode is definitely reverse bias. So then what happens to the circuit? So we can simplify the circuit. So we have capacitor here, we have a resistor here. This is reverse bias, so this is open then. So we have plus minus V out here. So this is already charged up to V naught. So we have RL here and C here. Now what happens to the circuit? Now we don't have this diode because diode is reverse bias, so we can simplify to a circuit where you can replace the diode with open circuit element. Now we will ended up with the kind of a circuit which we described previously. So we have a circuit where you have a source and a capacitor and a resistor. So for this RC circuit, we know that time constant, the product of RL and C is pretty much high. So then, whether this capacitor charged up to a voltage we know, this resistive load never gives capacitor to discharge through itself. Whether this capacitor is charged to V naught, so due to this high time constant scenario, so this capacitor never discharge the accumulated charge through the load resistor R. So during this cycle, capacitor is not discharged. Why? This RC constant is pretty much high. Whether this capacity is charged to V naught, due to this high RC constant, this capacitor never discharge. So it means like the charging remains as it is. So then what happens during this second cycle or this positive cycle? So this capacitor doesn't have any chance to discharge through the load. So the voltage stored in the capacitor as keep as it is. Now we'll move to the third cycle. So third cycle would be again a negative cycle. So then third cycle would be like this. So we'll discuss two cycles. So this third cycle. So third cycle, what happens? Now we have capacitor here. So we have a resistor here. We have a diode and RL. So now the applied voltage is like this. Your input is actually V naught. Now this capacitor is already charged to V naught. And you have a diode and a resistor. Similarly, you can now apply Kirchhoff voltage law to find what happens to the diode. So this is the voltage drop across the diode. So from this we can see, right? So we have V naught here, we have V naught here. So then once you apply Kirchhoff voltage, so V naught plus VOC minus V naught equals 0. So then from here we can simply say that the open circuit voltage is 0. So then the diode voltage will be 0. So from the very basics we know that VD is greater than or equals to 0 to make it forward bias if it is ideal diode. So VD is less than 0 to make it reverse bias. So then what happens? VD equal to 0. So at this situation, we can simply claim that, so depending on the previous step, for example, so 0 is the switching point. So then we can, someone can argue like VD greater than 0 directed forward bias, VD less than or equal to 0 directed reverse bias. So these both situations are possible with the previous step. So if your diode is in reverse situation in the previous cycle, whether the voltage across the diode is 0, it never gets on. Okay, so it means like the past state would be the reverse bias situation. Whether the voltage applied across the diode is 0, it never turns on. If your previous state is forward bias, it means this diode is already on. So once you apply a 0 voltage across the diode, that state is remains at is. It means like diode is still on whether the voltage is 0. So like based on that assumption, we can simply claim that whether the diode voltage is 0 during this previous cycle, we found that the diode is reversed, and whether it is 0, diode should be in reverse bias. So then we can simply remove the impact of this diode, because now the diode is reverse bias. So we can remove it using an open circuit element. So what about the voltage across the resistor VR? Now 0. So we have V here and V here. So we know that it never discharges through the RL. So the whatever the voltage appear across this resistor would be the output voltage. So we have V naught across the capacitor, and we have another V naught into the opposite direction due to the input. So the ultimate voltage across the resistor is 0. Okay. Then, so then we, if we go for the fourth cycle, it's a kind of a positive voltage appear across this one. So once this we apply a positive voltage again across the input circuit, so this diode is simply reversed. So it comes to a same situation like here. Diode gets reverse bias because it basically apply a negative voltage of 2 times V naught. So then diode is simply reversed. So diode is simply reversed. Once this diode is reversed, you can replace that with open circuit. So then the voltage across the RL would be now. So we have V out here and V out here. So we have 2 times V out. Okay. So we have 2 times V out. So then what happens to the output? So let's assume. So we have first negative cycle, then positive, like this. Here it's V naught, here it's minus V naught. So what happens during this first cycle? So during this first cycle, you don't see any voltage across the capacitor. So during this first cycle, because this capacitor voltage is zero. So this during this first cycle, during this block, so you have capacitor here, you have a load here, this is short circuit, and you have this kind of voltage. So this is zero, this is short, and this one. So during this cycle, capacitor gets charged. So but the output VRL is zero because this is already short. So this is your output, and this, the voltage across the capacitor immediately charged to V naught. So the voltage gets immediately charged to V naught. So then the next cycle, so we found that this diode get reverse bias. So diode get reverse bias, and this voltage is up here like this, and capacitor is all charged to V naught. So this is V naught. So this, then we found that so that is reverse bias, you have a voltage across the load which is equals to 2 times V out 2 times R. So during this second cycle, so this becomes 2 times V naught. So then again, third cycle, we found that this voltage is up here like this. So still diode is reversed. So then the effective voltage up here across the resistor would be zero because we have V naught, and this capacitor is still at V0 voltage. So then this output would be zero. So, and capacitor voltage remains at V naught. So then again we move to the fourth cycle. So then the polarity is something like that. So then the net voltage is simply 2 times V naught, so that is still reversed. So the net voltage is, and the capacity is still zero. So this is your input, this is your input voltage. So this is your output voltage, VRL. So this is your voltage across the capacitor. You see. So see what happens to the circuit. So due to this capacitor, so if you apply this kind of input, so it's actually shifted upward by V naught for this moves to zero. So this V naught moves to 2V. So it introduces DC offset of V naught. So it is simply shifted by V naught. So or else we can simply say that the output is actually clamp the input at V in at V0. So it means once you apply V0, this kind of a symmetric square waveform. So this clamper can clamp the input signal at V0. So it means, so it basically introduces a kind of a DC offset to the circuit. So then only you can push your input signal to this. So then the input would be, so input is actually in between V0 and minus V0. Your output would be at 2V0 and 0. So this clamping the input at V0. So this input is simply clamped or clamped at V0. So then only you can have a kind of a DC offset of the original input signal by V0. So then the output would be simply in between 2V0 and 0. Whether you apply a voltage of voltage which oscillate between plus V0 and minus V0, due to this capacitive effect, you can push this output voltage to 0 and 2V0. So what's the difference with, so if we consider the input signal and output signal, by looking at these two signals, we can simply say that input has 0 average. See, if it is symmetric over the t-axis, so if you integrate over the period, so we know that definitely the entire area would be 0. So the average of the symmetric waveform like this gives a 0 average. But once you add this capacitor, it basically introduces a DC offset. So then with this clamping, we can push the output to have non-zero average. So you can shift the voltage upward or downward depending on the configuration of the circuit. So this is the simple clamping operation. Okay, so we'll do the same for sinusoid. This is a bit complicated, so that's why we start from the square wave. So square wave is very pretty much straightforward. Once it is a kind of a sinusoidal signal, so we have several intermediate states. So we'll see how it's. So we'll again start with the same circuit. Okay, now we'll see this kind of a signal. Minus, plus, minus. Okay. So initially, so we'll apply this kind of a voltage. So this is V in. So during this block, during this negative cycle, the input is actually more from 0 to, let's assume this is minus Vm, this is plus Vm. So this voltage is simply moves from 0 to Vm and then again back to 0. So this is possible for both negative and positive cycle. So if it is a negative cycle, this voltage simply goes from 0 to Vm and back to 0. If it is positive, again like 0 to Vm and 0. So I am accommodating this direction by changing the polarity. So that's why I didn't consider this minus sign. Ideally, for the during this negative cycle, it basically goes from 0 to minus Vm and back to 0. If it is positive, 0 to plus Vm and comes back to 0. So if I accommodate this the negative values through this polarity change, so it basically change between 0 and Vm. Whether it's a positive cycle or negative cycle, it basically goes through the Vm from 0 to 0. Okay, so then if we consider this negative cycle, so this is scenario. So this is a negative cycle. So we have negative cycle. So this is Vm, this is 0, this is 0. Now see what happens if this input voltage moves from along this A to B. So A to B. So then here the input voltage is simply moves from increase from 0 to V. So we mark, so this is the diode drop. So initially the capacitor voltage is 0. So from this we can simply say that the voltage drop across the diode is simply V in, because capacitor voltage is 0. Vc equals 0. V in. So then this is during this A to B segment, your voltage simply moves from 0 to V, which is a kind of a greater than or equal to 0. So it's a positive value. So from this, we can simply claim that diode gets forward bias because we are applying a kind of a voltage which is greater than or equals to 0. At this point, the diode voltage is 0. At this point, your diode voltage is Vm. In between these two, so it's like less than Vm, but it's a positive value. So we can claim that during this half, this segment A to B, so we are applying a kind of a positive voltage across the diode, and diode get forward bias during this AB block. So if it is forward bias, so we know that diode becomes, so we can, if it is forward bias, we can simply replace this diode using a short circuit element. So then as in the previous, we can simply assume that the product of RL and C, this is pretty much high. So then you can't see any charging or discharging process through the load resistor RL. So then once this diode get forward bias, you don't see any current flow through the load resistor because it has a reasonably or comparably high time constant compared the circuit where through the diode. So then this through the diode, through the diode, tau would be close to 0. Through the RL, time constant would be pretty much high. So due to that, this current flow is only happens through the diode. So once this diode on, we can simply consider it as a short circuit element, and this capacitor get charged to V0. So during that, so I'll draw this input signal. So then during that, capacitor gets charged up to V0. So Vm. So this is A, this is B, C. So this is your input, and capacitor gets charged to its maximum, which is Vm. because we know that the input voltage is a bit increase up to Vm. So then gradually capacitor voltage reaches to its maximum, which is Vm. So in is actually we can simply claim that this is Vm sine omega t. Okay. Now this capacitor charge is to maximum. So then this is charged to Vm during this first segment A to B. Okay, so then what happens to the next? So now we'll consider this BC segment. So the voltage is input is actually start from Vm and moves to 0. Okay. So now what happens to the circuit? Now this voltage, now you input, the polarity is same to the downward direction, but the applied voltage is reducing to 0. Now here the voltage is reducing to 0. Initially during this point it's Vm. Once it moves along this and comes to here, the input voltage comes back to 0. But this capacitor is charged to Vm. So let's assume like what happens to the diode. So again, so this is same. Now in addition to that, we have this capacitor voltage. So if you apply Kirchhoff voltage law, we can simply say that Vm, which is the voltage across the capacitor plus the open circuit voltage or the diode voltage, minus or equals to Vin. Now Vd equals Vin minus Vn. So what happens to this diode voltage? Initially input voltage is at Vm here. So then Vd start from 0 because this is Vm minus Vm 0. So once this input voltage Vin comes to here, so then this is 0, it moves to minus Vm. So during this block, your Vd is actually in between minus Vm and 0. Minus Vm and 0. So it means like during this block, that get forward bias. During this BC segment, we are applying a negative voltage across the diode, so then it becomes reverse bias. So this BC segment diode becomes reverse bias because we are applying voltage in between 0 and minus 0. So diode is reversed. So once this diode is reversed, we can simply replace this diode with the open circuit element if we assume that it's ideal diode. So time being, we'll assume that it's ideal diode, so we can simply replace it with open circuit element. So then we have a circuit where you have a load resistor also. So then what happens? So then diode is reversed and it's open. So then we have a kind of voltage appear across the load, which is this is no longer be there. So then this RC constant is very high. So then the capacitor doesn't allow to discharge through RL. So whatever the stored energy across the capacitor remains as it is. So the VRL would be now VRL would be, so if you apply Kirchhoff voltage, VRL plus Vin equals Vm. So then this is equals to Vm minus Vb. So initially Vin is actually Vm. So then this is 0. From 0, once this Vin moves to 0, this becomes Vm. So during this block, so we have capacitor charge to 0. So this is short circuit. So then during this block, it's something like that. So once it comes to this segment BC, so that reverse bias, then the output voltage gradually moves to EM. So it's gradually moves to EM. Okay. So next, what happen? So now this negative cycle is already discussed. So we'll move to the positive side. Okay. So now we have this. So we have circuit. So this is already charged to Vm. Now this is the polarity. This is your input. So we'll mark this. So we'll take this block, consider the CD segment. So if you apply Kirchhoff voltage law, so we can simply say that Vm plus V in plus Vd, this is your Vd, equals 0. So then Vd is minus of Vm plus V in. So this is a kind of a negative value. So then during CD segment, diode is reverse bias because we are applying negative voltage. So diode is reverse, so you can't see any diode here. So what about the output voltage? During the CD segment, your input is moving from 0 to Vm. So then this output equals actually V in plus Vm. V in plus Vm. So Vin is gradually moves from 0 to Vm. So then this becomes Vm to Vm. So once your input is Vm, so this becomes doubles. So then your input moves to 2Vm and the voltage across the capacitor. So then again we'll consider this TE segment. So what about this time? So again we know that the voltage drop, and once you apply Kirchhoff voltage law, the equation or the relationship is still valid. Vd equals minus of this one. So then the voltage is initially V in is actually Vm. So then it becomes minus 2 Vm. So once it moves to 0, so then this is 0 again Vm. So the D voltage across the diode, actually voltage across the diode is in between minus Vm and minus 2 Vm. So then this is reverse bias. So this is reversed, and the voltage across the load would be like V in is initially Vm. So then it's at 2 Vm. Once it moves to 0, so then it's back to Vm. So this is back to Vm. Capacitor voltage remains as it is. So if you move it for, so if you consider the next cycle as well, so you can see this kind of a trend. If your input is something like that, your output is actually so your input is vary between minus Vm and plus Vm. Your output is basically more between C. So it's simply clamped at Vm. So this is simply clamped at Vm. So it's at a DC offset, at a DC offset of Vm to the input. Okay. So this is very simple, and so but the issue is like, so in the square wave, if your input is a kind of a square wave, you can simply consider the half cycles. So once it's in the negative and positive, you can easily get the output. But what happens if this input is sinusoidal within the half cycle? So you have to treat this whole half cycle with the two segments. Like in the previous case, we basically consider A to B and B to C segments separately, whether this cycle is a negative cycle. Similarly, for the positive cycle, we consider the two segments C to D and D to E separately. So otherwise we may miss some important facts inside the circuit. So this is the output of the circuit. So if we conclude this, what happens if we have this kind of a circuit arrangement? If you apply this kind of an input, you will end up this kind of output. If it is a square wave, so we'll end up with this kind of. Initially, there may be a kind of a transition period where this capacitor gets charged and make the circuit to produce the required voltage. So this during this transient period, your inputs and capacitor voltage may be different. Once this capacitor gets charged up to its maximum voltage, so due to this time constant constraint, this voltage charged inside the capacitor never discharge or charge it again through the load. So then the voltage remains as it is. and then you can have a kind of a steady state response. So initially, if you remember the previous cases, during this first half or first two half cycles, your circuit is not that steady. So inputs are giving different values, but after a certain couple of cycles or half cycles, you will get a kind of a same pattern as in the previous. So then you can identify basically during certain number of cycles, you can see it's a kind of a transient period. So after that, you can have a steady state. So if you ask to draw the output, so you just draw the steady state output. So this is the output what we are focused on. But if I ask you to discuss the circuit, so you have to treat both. So you have to show the show what happens to the circuit when the input is in transient state, or you have to specifically draw and explain the transient state as well as steady state. If I just ask you to draw the output, so you can just focus on the steady state and you can just give the output. If I ask you to explain the circuit, so you have to explain both what happens to the circuit during this transient and steady state. Okay, believe that this is basically give a kind of a briefing about the clamping circuit. So we have one more topic under this clamper. So it's related to voltage multiplier. So we'll discuss it in the next video. Okay, thank you.